Okay. Problem number 1 says a survey of an introductory statistics class in the fall asks if students whether or not they ate breakfast the morning of the survey. Okay. So we have gender. So we have male, female, and then breakfast is yes or no. And we kind of have this grid. My grid is kind of bad, but okay. So 66, 125, and then the total 191, and then the no is 66, 74, 140 total. And then we have the total over here for the yes no's. 132, 199, and 331. Is that right? Do you guys have that as your first problem? Okay. Just gotta make sure. All right. So what is the probability that a randomly selected student is female? Okay. So how many total students are in this study? 331. So you have 331. How many are female? Yeah, the 199. So that'll be the answer. And yes, you can make it a decimal if you want. You don't have to. Okay? I would just leave it as a fraction personally. Problem letter B. What is the probability that a randomly selected student ate breakfast? So B. So still we have 331. We don't have it as conditional in it at all. So we still have 331. So how many said they ate breakfast? 191. So you get 191 out of 331 for an answer. Is that okay? Then letter C, it says, what is the probability that a randomly selected student was male or ate breakfast? Okay. Now this is where we have to be careful. So randomly selected, so we still have 331, was male or ate breakfast. Okay, so we can't count the same thing twice when we're doing this. So was there males that ate breakfast? Yeah. So I can't count that category twice. So, okay, let's look at this. We say, okay, we have male. Okay, so that's going to be 66. Feel good so far? Okay. Or ate breakfast. So that has this here as well. Okay. Oh, I goofed a smidge. Hang on. I'm going to show you where I goofed. Let me do this. Undo. Okay. I'm sorry. Here's where I goofed. Okay. Males. 132. Ate breakfast. 191. Which part do I have to subtract now? Bless you. It's shared between the two. Nope. We're going to keep the 191. We're going to keep the 132. Is there a part that is male and breakfast both? Yeah. You're going to subtract the 66. Okay? If I don't subtract the 66, you're counting that part of your collection twice. Okay? I don't have a calculator with me. Fine. So we use the top drawer, but I always pick the second drawer thinking it's going to be different. So you got 132 plus 191 minus 66. So that gives us 257 out of 331. And again, if you wanted to, you could reduce it or you can make it a decimal. It's not necessary though, okay? Do we feel okay about that problem? That's a little bit different because I can't count the same region twice. Being we're talking about, hey, how many males were there? There were 132. How many people had eaten breakfast? There was 191. Who was a male and ate breakfast? There were 66, so we have to make sure we subtract that category. And that's a tougher one to think about. You just can't count that person twice. Okay? Sometimes if you have that kind of situation in statistics, that is a lot of time where an error would have taken place, where your data would be off a little bit because you counted some group twice in that situation. Okay. Letter D. What is the probability that a randomly selected female ate breakfast? Okay, so letter D, randomly selected female, and she ate breakfast. So let's see. Female, 125 of them ate breakfast. What is the probability of a randomly selected female? Okay, so we're talking about the female category. Okay, how many females are there in our study? 199. Okay, and then how many of those females ate breakfast? 125. Okay, so being that you're going to say how this study would work is you have your 331 people. You say females over here, and then you go over, okay, females, I'm going to pick somebody at random of you to see if you ate breakfast. So you're changing how your probabilities or your statistics is. You're eliminating part of the group in order to, and this would be like, who's wearing Nike tennis shoes? Okay, come on over here. Who's wearing a hat out of that group type of thing. Let's see, letter E. Letter E, what is the probability that a randomly selected student is female given the student ate breakfast? Okay, how many people ate breakfast? We had 191 that ate breakfast. And then what is the probability that, so how many of the people who ate breakfast were female? 125, right? Let's find a color I haven't used yet. I don't know. Orange sounds good. Okay. Like that, go. Letter F. All right, letter F. What is the probability that a randomly selected student ate breakfast and is female? Ate breakfast and is female, and it would be there. 125 out of that. Hey. So that's problem number 1. So does that work okay for vibrant stuff? It's when you have multiple categories and then you have a total of everybody. There's certain statistics you can run, but then, bless you, then other parts of it you have to go through and see if it works. So let's see. Do what? Yeah, you can make it a decimal. I just was leaving it as is.
Will they judge us on the test for that?
No, I'll give you either one. All right. I'll do both ways. Which means I have a whole bunch of answers I have to listen to.
Yeah.
So. All right. I want to flip over to problem number 4. Problem number 4 says during an inaugural season of Major League Soccer in the United States, the medical team documents 256 injuries that resulted in loss of participation of the player. The results of the investigation is shown in the table below. So this is on the back side. Is this okay? All right. So you have severity, which is minor, moderate, major, and total. We have practice. They were injured in practice or during game. And that total, so just make up our table. Okay, let's see. 66, 88, 154, 23, 44, 67, 12, 23, 35, 101, 155, and 256. Okay. So, does everyone understand what the table means? So, 66 people had a minor injury at practice. 88 had a minor injury during a game. So, a total of 154 people had some sort of injury, whether it happened during a practice game. And a moderate, major, same idea. As far as practice went, 66 had an injury at practice that were minor, 23 were at moderate, 12 that were major, so 101 had injuries at practice in whatever level, and then during the game, 155 had some sort of minor, moderate, or major injury during that. Okay? If an injured player is selected at random, find the probability that he missed a game. Okay, so letter A. So any of these injuries would result in not being able to play. And I get it. So you're like, well, you can play with a minor injury. We're just saying that if you have dictated with any of these injuries, you can't play. Okay? You know? Yeah.
They missed how many games?
Yeah.
256.
Yeah. Yes.
That's way more than one season. That's not even your whole.
I know.
Maybe it's like his whole entire high school
So this is this is all of the Major League Soccer throughout all of it. It'd be like taking the whole NFL or NBA. So that many injuries of the entire league. Okay, so the person missed a game. Okay. Okay, hang on. Is there anything? Result of loss of player position. The result of the investigation are shown on the table. If an injured player is selected at random, find the probability that this person missed a game. Hang on, I got to make sure I'm reading this right. The medical team documented 256 injuries. We have that in loss of participation of the player. Okay, so of the 256 injuries, how many of those injuries were out of a game? 155. So you had 155 out of 256. Okay.
That's
So
8, right?
was that
8.
That's should,
Yeah.
my thing's getting goofy on me. Need a sharp point on this. A little bit better point. 155 out of 256. Now some of you are just asking, should you convert those? This is easy enough to do on a calculator. 155 divided by 256. So 0.605, which would result in 60.5. What's the probability? Probability somebody missed a game.
Do we have some time?
No, I'm just showing you. Just to answer the question. I'm okay if you stick with this, but if you wanted to go all the way through, have some fun. How many? And then the next one says had a major injury. How many major injuries total were there? How much?
256.
Major injuries. How many major injuries were there?
35.
35. Okay, so you had 35 out of the 256 total. Okay, and we weren't trying to find if it was during practice or a game that was a major injury. It was just total injuries or total major injuries divided by total injuries. C, had an injury that was minor or moderate. Had a injury that was minor or moderate. Okay, so you would add up those three I just circled. And that would give you 66 plus 88 plus 23 plus 44. That's 221 out of 256. So letter C, 221 out of 256. Okay. Let's see what else. Missed a game and had a major injury. So we now are missing a game. Let's extend this page a little bit. Missed a game and had a major injury. So missed a game, had a major injury. So major injury and missed a game. So major injury and missed a game. It's talking about this person right here. Okay, that game was missed. How many major injuries were there? How much? 35. So letter D, which is down here, is we had 35 total major injuries, and of those major injuries, 23 people or 23 games had been missed by those players somehow. A, B, C, D, E. Okay, he missed a game given a major injury. Okay, so there's going to be a little flip-flop. Missed a game. Oh, okay. How many games were there? There's 155 as far as the injuries went. So there's 155 games missed by players, and 23 happened to be, so you had 23 out of 155 there. Okay, so that's talking about how many people had missed a game, and then being they had this type of injury. Okay, F, he had a minor injury given only missed practice. So minor injury, how many practices were missed? How many practices were missed total? 101 and 66 for minor injuries. So F would be 66 out of 101. G had a major injury, injury or missed practice. So this is one of those we will have to subtract a group. Okay, had a major injury or missed practice. So we're going to still be out of 256. Okay, so how many major injuries were there? How many major injuries were there? 35. Plus, how many, and I'll even have to have the whole thing up there, how many missed practices were there? 101, and this is going to work out perfect. How many of those do I have to subtract because it was a major injury? My goodness, I don't know what's going on with me. It was a major injury, and they had missed practice. So how many people do I have to subtract? I don't have the whole grid up there for a reason. No.
25.
So, 12. Thank you. It's one of the numbers. Okay, so this group would be counted twice if you left them in. Okay, so don't count them twice. So then if you do your math, let's see. It's going to be 124. I believe it's 124 out of 256. If I did that math right. I was trying to do it in my head, but I goofed up. All right, we okay?
Yeah.
Sweet. So, and again, these can get a little goofy. Sometimes they are weird to wrap your head around, and that's why I try and go slow with it and have a little goofy fun with it. Huh, okay, cool. All right. Whew. All right, let's do some notes. This kind of seems like a thicker packet I'm handing out to you. The reason is I have the
We're gonna pass this up.
No, I will. I'm just kind of putting points in if you're here. Being we are so close to the end of the semester, it just becomes a grading nightmare to throw everything in. I haven't put the stat stuff in yet. I will. So it's coming. Okay. What you got? Oh, thanks. I'll put that in for you. What period? Okay, I'll be in my office down the hall. Cool. Thanks, Sammy. Let's see. Let's go to the front of this. Here. All right. Come on, baby. All right. More probability. Talking about Venn diagrams and tree diagrams. And I think some of you might appreciate these because they're a lot more visual than just looking at a grid. Okay, so let's see. Disjoint events. Okay, disjoint events. Two events that cannot happen at the same time. So that would be something like if you had a deck of cards and you were to select one card out, what's the probability of pulling a king and a 10 out? If you're only pulling one card out, you can't pull a king and a 10 out unless they're stuck together, right? So that's kind of a cheap version of the disjoint event. Conditional, probability of one event happening given another event has already happened. Okay, so those are just what's going on. And those definitions were already available for you, yes? Cool, good. Okay, we'll move on. All right. Let's see. A survey. Oh, this is kind of goofy. Is that on yours like that too? It's kinda... Okay, so I'll have to move that out of the way eventually. Let's see. All right, so
Maybe you have to slide them over the bottom. I always would like that on our paper.
yeah, I was just trying to clear it up so we don't have to deal with it on mine. But sorry, you can't hit return on your paper. All right, let's see. A survey of 350 CCHS students was taken to see if they have started studying for finals yet. The results are shown in the segmented bar chart below. Use the chart to answer the following questions. So it appears, as far as ninth graders, 35 said yes, 50 said no. 10th graders, 60 said yes, 35 said no. 11th graders, 65 said yes, 35 said no. And seniors is almost an even split with a 40 said yes and a 30 said no. Okay? So you understand the event that's taking place? I know it's kind of a goofy event, but let's just act like we're good people and think it's good. All right, we are good peoples. All right. How many students surveyed were ninth graders? 85? Okay. Does that make sense? Okay, now I'm not looking for the total. I'm just saying, it just says how many people who were surveyed happen to be ninth graders. I took the 50 and the 35, added them together. How many students have already started studying for finals? So then we're going to add up the blue groups. So 35 plus 60 is 95. 95 and 65 is that 150 plus 160? Hang on. I'd be a much better math teacher if I could actually do arithmetic. It comes out to what? 160? 35 plus 60 plus 65 plus 40? Whoa. 40 plus 65 plus 95? Is it 200? It's 200, right? So 200 students started to study for the finals. If you were to select a random student, what is the probability that I pick a 10th grader that has not started studying? So how many 10th graders have not started studying according to this?
35.
35. How many total students were in this survey? 350. Okay. Yes, you could reduce that. It becomes 1 over 10. But, just leave it that so you can see where the numbers are hanging out. Okay, letter D. If I were to select a random student, what is the probability that I pick a 12th grader? So how many 12th graders are in this study?
Oh, my fault.
70, right?
Exactly.
Okay, so 70. Oh, I'm going to squeeze it over here. So 70 out of the 350. Again, you could reduce that to 7 over 35, which reduces to 1 over 5. Letter E. If I were to select a random student, what is the probability that I pick someone who is either 10th or 11th grade? So how many 10th graders are there? 95. How many 11th graders are there? How much? 100. So 190. So letter E, I'll bring it right here, is 190 out of the 350 because it was the total of both. I'm on letter F. If I were to select a random 12th grader, okay, so we're just worried about the 12th graders, what is the probability I pick somebody who is not studying? So letter F's answer, I'll bring right here because it's next to it. How many seniors were there? 70. And then how many did not start studying? 30. So 3/7 didn't start studying yet. If you wanted to reduce it, I'd keep it as that. Okay. And then letter G, that says if I were to select a random student that has been studying, what is the probability that I pick a senior? Okay. So how many people appear to have studied? 35, 60. Didn't we do that someplace?
Yeah.
How much is it? 200. Okay, so the very last one, so G, we have 200 on bottom, and then so it's like, okay, all of you that studied, get over here. Oh, they all get over there. What's the probability of those 200 people that you pick a senior out? How many seniors are in the studying group? 40. And again, you could reduce that to 4 over 20, which is 1/5 or 0.2 or whatever. Woo! Is that okay? Seem okay? And it's just a matter of if you can start eliminating portions of your statistics to get your information that you're looking for. Is that right? May I move forward? Sure. All right. When you have multiple events with conditional probabilities, a tree diagram might help visualize the situation. Multiply across branches and add up multiple branches, okay? So before we start the tree diagram, a few things to know. Each branch, if you sum it up, has to sum up to 1. Okay, remember statistics goes between 0 and 1. Each branch, as you lead out further and further, you multiply those branches together to get to wherever the end of the branch is. And once you're at the end of each of those branches, all of those have to add up to 1. Okay, so you're just going through and deleting events. Okay, so this says that a certain disease is present in 0.005 of the population. Okay, so for those of you who want to know how much that would be, if you had 1,000 people, 5 people would have this disease. A new blood test has been developed to test for the disease. If you have the disease, the blood test is 98% accurate. 98% is accurate 98% of the time. If you don't have the disease, the test is accurate 97.2% of the time. Find the probability you have the disease given you tested positive. Okay, so let's talk about a couple of things that are terminologies that might take place. So you have this disease that takes place in a certain amount of the population. It's 0.005 people, which comes out to 0.5%. So if you wanted to, you could say, well, this is 0.5% of the population. If you wanted to say that, just sometimes it makes it easier to think about. Okay, of this disease, if you go and have this blood test and you happen to have the disease, 98% of the time they are correct with their findings. There are 2% of the findings in this test that they do that the person has the disease, but the test came back negative. Okay, and then if you don't have if you had the blood test done and you don't have the disease, 97.2% of the time they will say, "Yep, you're good." But there is a 2.8% of the time if you don't have the disease and they test you, and you don't have the disease and they test you and they show that you do have the disease. Okay, and that's things that do take place in the medical community. There's nothing perfect about medicine. There's not a one-size-fits-all for everybody as far as medicine, so you start relying a lot more on data and information. So our very first piece of data, and yours might be really hard to see. I don't know, can you see those? Okay, so I need to write these alone. So you have your person. So your person, you have 0.005 has it, or 0.995 doesn't have it. Now, here's where I need to have you clarify. Okay, so for each branch that we go at, if I add the branches together, if I add those branches together, I need to come up with 1. So it's 0.005 plus 0.995 equal to 1. Does that make sense? So let me change color now because I'm going to a different branch. Okay? So 0.05 has a disease, and they said that 98% of the time it works, and 0.02% of the time it doesn't work. Okay? So you're right. This one little branch here is 1. That's good to see. So what you should do is then you take the 0.005 and you multiply it times the, so 0.005 times 0.98. So this up here is 0.0049. Okay? And let me fill the rest of this out and I will tell you what this number is going to mean in a moment. And then you take 0.005 and you multiply it by 0.002. 0.005 times 0.002. And that means that 0.00001. Boy, did I do that right? Okay.
Mr. We have to multiply it?
Yeah, you want it. So you want to multiply this times this, this times this. So you do a multiplication here, and you do a multiplication here to get to the next set of branches. Okay? And then I'm going to do the same thing here. So I'm going to go to the 0.995 times the 0.028 because there's the 0.028 that doesn't have does not have the disease but is tested with it. So 0.95 times 0.028. So this result here is 0.02786. And then the last one is 0.995 times 0.972. Did I do that right? Yeah. Okay. Which this one is going to be 0.96714. Now, if I add all of these up, if I add this new streak of branches, so again, this was multiply here to get to that one, multiply here to get to this one. If I add those branches up, so 0.0049 plus 0.00001 plus 0.02786 plus 0.96714. If I add all those up, I come up with 1.000 or 1. Okay? Is that all right so far? So let me just verify I have these right. 0.005 times
You add every single one.
0.9. Well, you want it. That will tell you if you have the tree diagram done correctly.
Yeah.
So each branch. So 0.98 times 0.05. Anyone have a graphing calculator I can borrow? Thank you. Sometimes when you start dealing with bigger decimals, they get a little goofy in my head. 0.005 times 0.98. Yes, got that right. 0.005 times 0.02. Oh, this decimal's in the wrong spot. This one should have been 1 decimal less. That works now. Cool. All right. Thank you. All right. And as far as this goes, so when you start thinking about this, if I were to convert this to a percent, 0.49% of the time, somebody has the disease and they tested positive. And then you go through and you were to convert all of these into, so this is 0.01% of the time. You're talking about small things. And then this is 2.786% of the time. This one is the big one. So this is 96.714% of the time. That's how all of this takes place. So that's just a tree diagram in its best. And I have one slide left and then a Venn diagram. So, well, it's just going to be take a look at it. And, if you have the opportunity to try it. So, again, the tree diagram, I did it in 2 different colors. So your first branches are 0.005 and 0.995. Those add together to give you 1. Your next branches are you multiply the 0.05 times the 0.98. You multiply the 0.005 times the 0.02. Multiply the 0.995 times the 0.028. You multiply the 0.995 times the 0.972, and you get those. If you add those values up, you wind up with 1. I just converted them to a percent. Sometimes that becomes nicer if people do that, but it's not necessary. Okay, so that's just the diagram of how this would work, the separation. So somebody who is carrying the disease, so what's the probability that you have your population who has the disease that tests positive? That happens 0.49% of the time. You have a 0.49% chance of happening. Okay, so that's a pretty low population. All right, last slide. Okay, the probability of a student that belongs to a club. So we'll call this, the blue one, we'll call a club. The other one, the probability of a student that works. Okay, works part-time. So the probability of somebody that belongs to a club is 0.4. The probability that a student works part-time is 0.05. And the probability that the person is part of a club and works part-time is here. Okay? So if I were to say the probability of being part of the club is here and part-time work is here. So if I add 0.4, 0.05, and 0.5 together, I come up with 0.95. What can we say about the other 5% of the population? What can we say about the rest of the population? The last point. Let's see. Last 0.05 doesn't belong to anything. So what is the probability that a student belongs to a club or works part-time? 0.4 plus 0.5, that's your or. It's the outside, which gives you a 0.9. Okay? So the third page is statistics part 3. If you get the opportunity, I think you might be able to do quite a bit of that. We'll go over it on Monday.
Where's an algebra? Oh, yeah.
See the very last page?
Yeah.
Other than that, I'm done. Have a good day, everybody.
Mr. Turtle?